Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a radical complex equation. Radical equations are fun, complex equations are fun. Let's go ahead and mix it up. So we have z times the square root of z equals 2 root 2 plus 2 root 2i. I remember making a video on a similar problem. I hope I haven't made the exact same one. Sometimes that happens because I have so many problems on the channel that I kind of lose track. And I have another channel called Cyber Math, Cyber with an S, where I do number theory and algebra problems. And thinking about a geometry problem, haven't found a good one yet. If you have any good ones, suggest, but don't make it too hard because I'm not very strong in geometry. Okay, so let's go ahead and see how we can solve a problem like this. I could probably talk about two different methods, maybe even three, but they don't all have to work, right? For example, one of the methods that I thought about was maybe replace z with a plus bi. But then we have a problem. Houston, we have a problem. What is the square root of z? It's the square. It is this, square root of a plus bi. But what is the square root of a plus bi? There's a formula for it, which involves something like this, I think, right? Something like that, and then we radicalize it, and plus minus something, and there's an I here, so on and so on. Quite complicated, and I don't think it's going to help you solve the problem. That's really going to make things super duper complicated. So this is probably not a good method, but if you do think it's going to work, let us know, and just let us know what you think overall. So another method, maybe this is not good, so let's call this the next one. First method is squaring both sides, and the reason we do that because we have a radical. Okay. Let's do it. So I'm going to square this and I'm going to square that. But before we do the squaring, I think we should simplify this a little bit. Maybe like take out 2 root 2 so that you can square a product. And this will just become, when you square it, z squared times z, that'll be z cubed. In other words, z root z is the square root of z cubed. Get the idea? Okay. In a complex world, you have to be careful though, because when I write square root of z, a complex number has two square roots. But when you use the square root sign, just like a real number, for example, when I say square root of 4, nobody's going to understand, oh, it could be plus minus 2. No, there's a definite answer, unique, well-defined as 2. So to agree with that notion, with complex numbers, we need to talk about something called principal square root. And that's usually the one with a positive real part. Maybe a non-negative real part? Can it be a zero real part? Yeah, I guess. When that's purely imaginary. So we're going to stick to that. At the end, we may need to check our work, but let's go ahead and do the work here. Z cubed is going to be, if you square 2 root 2, you're going to get 8, and then this will give you 2i. Nice. So from here, we get z cubed equals 16i, and then I need to cube root both sides to solve for z. How do you cube root this? There's a couple ways to go about it. I don't think you want to use one of the methods, but I'll still tell you about it. Yes, you can replace z with a plus bi. I mean, there's no harm. Let's just use it real quick. You got to know how to expand it. And the formula I use involves cubing this and then cubing this and then plus 3ab. Notice that I cubed is negative I. That's why there's a minus sign. Plus 3xy times x plus y. Okay, it's going to go like this, okay? And then if you distribute, this is going to give you 3a squared bi, and this will bring you minus 3ab squared. So I kind of have to pair these up. This is the real part, and this is the imaginary part. Be careful with the plus minus signs. A lot of times I miss it. I make mistakes. You probably know. So that's my z cubed, and I want that to equal 16i. You know what that means? That means that the real part needs to be 0. So this needs to be 0, which is good. I'll show you why. If it wasn't 0, then it will be a little harder. But in this case, it's really nice. And then my other equation is going to give me 16, right? Because that's the imaginary part. Let's go ahead and write this as a system. This is a really nice system, by the way. And we can solve it by replacing b with something like at. Okay? Bat. Okay, so if you replace b with at, From the first equation, you get a cubed minus 3a times a squared t squared equals 0. And this gives us a cubed, so we can factor that 1 minus 3t squared equals 0. If a is 0, then b is 0. But that doesn't work with the second equation. They can't be 0. So a can't be 0. Okay? So this has to be 0. That's a must. So 3t squared equals 1 implies t is equal to plus minus root 3 over 3. Just like the tangent of 30 degrees and what's the other one? Subtract from 360, 330. And there's another one, the second one. Anyways, you get the idea. That's my t. And what am I going to do with that? Replace t with that. So b is equal to, let's just use the positive one. So like this. And then, of course, you can plug it into the second equation. 3a squared b minus b cubed equals 16. Did I copy that right? And then replace b with that. We could probably do the following. 3a squared times, oh, you know what? Did I use the first? Okay, never mind. I haven't used it. So root 3a over 3 minus, if I cube it, if I cube this is going to be 3 root 3. If I cube this is going to be 27. So it's going to be like q root 3 over 9 times a cubed. Okay, I got it. So this is a cubed and this is 16. So I'll take out a cubed. 3 cancels out. I get square root of 3 minus square root of 3 over 9 equals 16. This is 8 root 3 over 9 times a cubed equals 16. 8 goes into 16 twice. A cubed becomes 18 over root 3, which I can write as 18 root 3 over 3, which is 6 root 3. And then to find a, I need to cube root it. I don't think there's a nice way to cube root it, so I'm going to write it like that. And b is just going to be a times t, which is this. A times root 3 over 3, a times root 3 over 3, okay? There you go. Since z is equal to a plus bi, then you can write the solution, right? Easy. Okay, cool. Now, what about the other method? I think the other method, you'll probably like that better. So instead of dealing with this type of complication, because we really overcomplicated things, but I want to show you something that works, and it's kind of long, but that's okay. I like alternative methods, right? So here's the second approach to this equation. I can go ahead and write this in polar form. 16i is imaginary, so it's going to appear here, 16 units away from 0, which is its modulus, and then the theta, which is the argument, is going to be pi over 2. Of course, we can now write this as 16 times e to the power I pi over 2, but I got to be kind of careful because we need to add multiples of 2 pi, because there are 3 cube roots. We only found one of them, right? Well, actually, did we find all of them? Yeah, just one of them, but the others are going to come up from the other values. So here, we can go ahead and raise both sides to the power 1/3. That'll be 16 to the power 1/3. And this will be divided by 3. So I could probably do it as follows. 4 pi n, maybe I should keep the same order. Pi plus 4 pi n, divided by 2, but then divide by 3, so that'll be 6. Now you can go ahead and replace n with 0, n with 1, and n with 3. That should give you 3 solutions, because there should be 3 cube roots. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.